Okay, we move to Chapter 5, Spatial Data, and we will work with world map projection. We will talk about it and work with the US map projection and the project coordinate system. PCS, learn about vector data formats, download US census map layer and tabulate data, explore, download, and process data from living atlas of the world, explore sources of spatial data from government website, and explore maps from a university web service. The most important information that maps and GIS provide is location. So where is an object or event positioned? Is the object on a major street with good access? Is there a barrier to accessing it, such as a river? Is it a certain area where the similar things position? What or who is near it? These are some of the questions that maps can answer. So where you sit right now has two unique numbers, latitude and longitude coordinates that pinpoint your location precisely on the surface of the Earth. So now we will learn some useful facts about latitude and longitude coordinates and the geographic coordinate system that they are comprised in. And we will learn about the map projection, making flat maps from the nearly spherical Earth, basically just transform from 3D to 2D. We can project maps in at least 100 ways. Sometimes what projection you choose makes a big difference. So we will put some guidelines to how to choose the projection, and we will change the geographic coordinate system to a projected coordinated system by setting the map properties. And for the continental level, we will change the projected coordinate system to a different projected coordinate system by setting the map property. And we will set projected coordinate system state plane for a local level map by adding a first layer to the map, and then specify the display units for the map, and we will add a second layer which has geographic coordinates and see how it is projected on the fly to the state plane coordinates. Finally, we will change the geographic coordinate system for a state level map to use a projected coordinate system UTM by setting the map properties. So the key input of GIS is geospatial data, digital data that represents and can be rendered into maps on a computer. So we may collect some original geospatial data by ourselves, but more likely most, if not all of the map data will come to external organization. We will collect area imagery, roads, population, and other map data that we will use. The answer is that international organizations and federal, state, or local governments collect the data and will provide it to you at little or no cost, increasingly as download or service from the internet. The Living Atlas of the World, available in ArcGIS Online, is one of the foremost sites for obtaining such data. We will explore the Living Atlas and other US federal sites here. And the first part, we're going to talk about the map projection, but we will look at the big picture here. So working with the spatial data, and we are learning spatial infrastructure, the first one is talking about map projections. So map projections is a way to represent the curved surface of the Earth on the flat surface of a map. It's transforming from 3D to 2D. You can just simply think about this. And hundreds of map projections, and each map projection has its advantages and disadvantages. Again, not a single projection is perfect. So depends on the scale of the map and depends on the map's purpose. Different projections good for small areas with a large east and west extent, or areas with large north and south extent. So for the map projection, features are projected onto one of three developable surfaces. So no distortion where surfaces touches Earth. Secant projection if surface pierce Earth. And transverse projection if rotates 90 degrees, and conformal projection, cylindrical projection using a cylinder tangent at the equator, and parallels and meridians at right angles and shape of small objects preserved, the size, shape, area of large objects distorted, scale approaches infinity at the pole. An equivalent projection, conic projection, uses two standard parallels. Scale and shape are not preserved, but distortion is minimal. Distortion is minimal. Let's see, where do we go? And we talk about this. So right here we're still on Mercator. So Mercator, it starts very early, 1569. So the parallel and meridian at right angles preserve the size, shape, area, large object distorted. Scale approaches infinity at the poles. So you can see Greenland and everything is so huge. Russian is huge, and everything is so huge. An equivalent projection, conic projection, uses two standard parallel. Scale and the shape are not preserved, but distortion is minimal between the standard parallel. Best suited for east to west land masses. So, for example, Albert's equal area. Compromise projection, either conformal or equivalent. Meridians curve gently, avoid extremes. Doesn't preserve properties but looks right. And cartogram, the person's name, I forgot his name. Danny Darling. Yeah, Danny Darling. He did a lot of cartograms, so we're going to talk about the cartograms, Danny Darling. And if you search for his TED Talk, it's a good source to look around for his information and about cartograms. So geographic access to high capability, severe, accurate. So the SAR failure center in the United States. So in Florida it's good, in those eastern areas it's good too, and some areas just bad. So look at XY coordinate system, spherical coordinates. So geographic coordinate system, GSC, spherical coordinates, angles of rotation of a radius anchored at Earth center, and we have 80 longitude and 40 latitude. So the latitude, longitude we can say meridionals, and longitude prime meridional, you have east and west. And latitude is just equator, 0, and to the north and to the south. Those you can learn in World Regional Geography 1 and the very basics. And degree, minutes, and seconds, that's how we describe. And for example, Pittsburgh, Pennsylvania is 40 degree, 26 minutes, and 2 seconds north latitude. And for the longitude, you would say 80 degree, 0 minutes, or you can just say skip 0 minutes and you say 58 seconds. West longitude, Adelaide, Australia. If you are using Google Map, you put the coordinates there. It doesn't use the minutes and seconds. It's just like maybe 34.98 south. It will be negative, and for Pittsburgh, for west, by default we will use negative in Google Map. And then that's how I mentioned in here that if in the southern hemisphere we will use negative number, and if it's in the west, to the west of the prime meridian, and you will use negative. And that's how we we will just use the minutes divided by 40 by 60, and you get the point something. So if you use Google Map, you will let me just do a quick demo. So quick demo, Google Map. So let's just go to Sydney. All right, Sydney. Australia. Okay, so now you will see it changes the latitude and longitude. Latitude is in the south hemisphere, and it's east to the prime meridian. It's 150. Okay, now we're going to do is back in our slide. So the world circumference through the pole is this much. So for latitude, 1 degree is around 70 miles. In 1 minute it will be 1.5 mile, and 1 second it will be 100 feet. The length of the equator is this much. Wow. So coordinate system x, y, z, so rectangular coordinate. And we will go for the Cartesian coordinates, x, y, and that's two-dimensional. We will plot the latitude and longitude there. So state plane coordinates. So state plane coordinates established by the U.S. Coast and Geodetic Survey in the 1930s, used by U.S. local governments, all positive coordinates in feet or meters. Originally North American data, AMD to 1927, more recently NAD 1983 and 1983. High accuracy reference network, high accuracy reference network. So we have 125 zones, at least one for each state. Cannot join projected zones to make larger regions. Follow state and county boundaries. So each zone has a projection. Lambert convert east-west orientation, but it's transverse Mercator, it's more a north and south orientation. So some Lambert conformal, and Mercator. And state plane Pennsylvania South layer, for example, city of Pittsburgh sidewalks, and feature provided by City Planning Department, NAD 1983, FIPS 3702 feet Lambert conformal comic projection, and state plane Illinois last layer Chicago parks and buildings, features provided by Chicago, City of Chicago, NAD 1983, FIPS 1201 feet transverse Mercator projection. And then you can see from the lower left hand side for the information. So for ArcGIS Pro, option sets for coordinate system for new maps that we can just go to map, and same for neighborhoods state plane add first, so the data frame x coordinates will be state plane. And the UTM rectangular coordinates, so developed by U.S. Army Corps of Engineers during the 1940s, used by U.S. military and federal organizations. For example, USGS covered the world 80 degrees south to 84 degrees north. Metric coordinates, stay-tuned transverse Mercator projections for longitude zones 6 degrees wild. Coordinate system for ArcGIS story maps recommended WGS, World Mercator, and Auxiliary Sphere. General guidelines for publishing story maps. So we already did that. So keep all objects ID and shape fields visible in all layers. Open fields view and make sure those fields are checked. So we will give the map and all map layers the WGS 1984 Mercator ancillary sphere projection, or make the maps and all map layer have the same projection, and use the project tool to change projection of a map. Click click project option map and sync to change